Okay, it is my great pleasure to introduce this morning's seminar speaker, Dr. George Karniadakis, who is the Charles Pitts Robinson and John Palmer Barstow Professor of Applied Mathematics and Engineering at Brown University. To get a small sense of the accomplishments, he has an H-index of over 100 and has recently been elected to the National Academy of Engineering and other accolades. His research is in a very timely, or at least the research he'll talk about today, is in a very timely field, combining some traditional mathematics with the modern vogue of machine learning and advanced statistics across multiple scales applied to biology, something we're all interested in this department. And you know he's a serious thinker because there's a quote by Richard Feynman on his website. So please join me in welcoming George. Thank you very much for being here.
Thank you, Zachary. Thanks for the invitation to, sorry I couldn't travel, but I haven't traveled through the pandemic, and so I'm still very conservative, unlike the Floridians who are very brave. Today I want to talk about this topic of how one can integrate machine learning and multiscale modeling in biomedicine. And just before the pandemic, we had this workshop at NIH. And in fact, we talked about this topic. And what you see here on the cover page, where you see the this axis of data. There is another axis here of physics and ODEs and PDs and so on, a theory. And in the middle, you see the multiscale modeling with the cartoon and also the machine learning sort of shaking hands in some sense. Now, those two areas could actually work synergistically, and that's my objective today, to show you how could this be done. Of course, we all appreciate that with multiscale modeling, one can identify causality, can predict the system's dynamics, can elucidate mechanisms and the emergence of functions, and bridging the scales, something that is very common in biophysics and biomedical systems. On the other hand, machine learning can explore a massive design space, can identify correlations, that's sort of the inputs, outputs, that's what you're doing, can quantify uncertainty, and even solve ill-posed problems, and that we cannot cannot tackle with conventional methods of scientific computing. So these are some of the topics. So I want to show you the synergy, and what I mean here, machine learning and multiscale modeling is the use of neural networks and other techniques which allow us to do image informatics, bioinformatics, extracting quantitative information, which together with the laws of physics, what I call here mechanistic modeling, could work synergistically for classification, for prediction, inference, and so on. Okay, so let me start with an example. This is something we did a few years ago now. It's the first use of convolutional neural networks in a disease that I have a grant for NIH with MIT and French researchers on sickle cell anemia. Sickle cell anemia, of course, is characterized by this deformed, heterogeneous red blood cells. And what we did in this project is to design a convolutional neural network that takes images of a blood stream of a sickle cell patient. And we were able to identify various classes, or up to 8 different classes of deformed cells, sickle cells. Now, the disease is called sickle cells, and sickle cell disease, and you'll think that this type of deformed cell it's the prevailing one. But to our surprise, we found that using this method, where we can automatically detect large populations of cells, we found that these sickle cells are actually only 20%. In fact, the minority is the sickle cells. Most of the other cells have other shapes like these echinocytes, which basically reflect a different polymerization of hemoglobin inside the red blood cell. So now, how do you use this synergistically? Well, first we use this to identify what the problem is. Then we go back to the drawing board and say, okay, why we have these mechanisms. And therefore, one can explain, for example, that the different shapes are related to different deoxygenation rates, which are, of course, characteristic in this disease. So this is an example of how one could use image informatics together with mechanistic modeling. Moving on to diabetes and diabetic retinopathy, you may know from relatives or other friends that those who suffer from diabetes 2, for example, they have this vessels, lots of red vessels in their eyes, but also these microaneurysms. There's a myriad of microaneurysms, in fact, in the diabetic eyes, as you can see here, and usually they appear as small dots because they have size of about 10 to 100 microns, very, very minute. However, new technologies, this is based on what's called fundus technique, but now new technologies with our collaborators from the Joslin Center at Harvard University, with adaptive optics, they are able to identify the three-dimensional structure of this. So by doing that, you can see here, you get again a plurality of different shapes of these microaneurysms, and of course the question is which of these microaneurysms are amenable to rupture or more likely to rupture, and not all of them. There are about 5 different classes, and some classes are different than others. Now, for a researcher to identify that, it takes a lot of effort because, as you can see down here on the left bottom, there's a forest of vessels, and there is some tiny spots which are the microaneurysms and so on. So what we did is to develop an automated procedure of doing that. So the technique that our collaborators from Joslin Diabetes Centers developed is called adaptive optics scanning laser ophthalmoscope, or OWSLO. So we developed the OWSLO net, which is based on CNN, just like I showed you before, but it has this kind of U structure, what's called the U-net. And one of the difficulties dealing with this type of images is, as I said, you're looking for a needle in a haystack, because you have a very tiny microaneurysm in the forest of vessels, and of course you have images which are out of focus, and you don't have enough patients. So you always you don't have big data. People talk about big data. Big data is only in Facebook and social media. In science and biomedicine, as you know, we have little data. So you have to improvise with proper data augmentation techniques. So that's what we did in this OWSLO net. We took the images. We have about 100 patients. We salvaged 70 images from both eyes. And then we're able to, with some processing, to automate this. And now the clinician can use this OWSLO net. So just going directly from the images, as I said, the fundus images, something like that, there's not much you can do. But the new techniques, the OWSLO images, look like that. You still need a lot of work to clean them up and automatically identify like that. So now what you do if you find them, then you can again go back to modeling, to multiscale modeling. And here we show a real microaneurysm, but the flow is synthetic. It's a computational method of using coarse-grained molecular dynamics, for example, where we have these platelets that come in and they form a thrombus in this region, as you can see. These are the thrombosed, activated and then thrombosed platelets, which will form this plug at the wall. And at the end, we get the size of the plugs here, different cycles of the flow. And we can compare with experimental data from experimentalists. So now we have developed a sort of prognostic tool, if you like, going all the way from identifying the different geometries to simulating to sort of pose the question, when will this rupture? And because now we can compute all the forces on the wall, and we just need to know the tissue and and the rupture, the yield stress. Okay, so from small aneurysm, from tiny aneurysms to giant aneurysms in the brain, what you see here is a brain vasculature. It's a work done with Children's Hospital in Boston with neurosurgeon Joseph Madsen. We did this more than 10 years ago. We tried to simulate the entire brain vasculature, and at the same time, we're looking at a tiny part of the aneurysm, this dilation in one of the arteries, and we're doing this multi-scale simulation. In other words, we're looking at the flow. This is the circle of Willis. If you have not seen, then we are zooming in here. So we're basically using the continuum Navier-Stokes equations for the flow. But then, because we are interested in the rupture here at the apex of the aneurysm, we use molecular dynamics methods to zoom in, so to speak, literally. And then we have coupling of the two. Now this was a hero computation, was done on 300,000 processors at the time, more than 10 years ago. And we actually were the finalists in this international Gordon Bell supercomputing competition. Unfortunately, that year we were beaten by the Japanese. We came up with a new fast computer. But so unfortunately, although it was interesting academic exercise, we didn't learn much. At least the clinicians didn't learn much from that project, because what the clinician sees is something that you see in this black and white video. Basically, what they do, the neurosurgeon will inject some contrasting agent, some dye, and then he or she will observe the circulation of the flow inside the aneurysm. And then, without any guidance, any quantitative criterion, qualitatively and based on their experience and their gray hair, they would say, okay, well, it's time to intervene, to put a clip, to do an operation, to do a coil, to put a coil, and so on. So that is really very qualitative. So we asked ourselves, can we use this information, the dye visualization, to extract quantitative information that we can pass to the clinicians on the severity of the stresses on the aneurysmal sac, and when will this aneurysm will rupture? So that's, of course, the $1 million question. We'll address it in a little bit. But before that, to get there, I want to tell you something about another aspect of machine learning, which my group is very well known for now, and that is the physics-informed neural network, and how we take data and physics, biophysics, biomechanics, other laws that we can express mathematically, prior knowledge, and to put them together. So in most of the time in engineering and in bioengineering, we have this scenario here that I have in the middle, where we know we have, let's say, a advection diffusion reaction process. Most of the times we'll know how to do to express diffusion and advection. We don't know how to deal with reactive transport, for example, coagulation cascades in thrombosis, because these reactions are not well known. There's hypotheses and so on, but there's no consensus. So, however, we may have some data in vitro, some data in vivo, and so on. So the scenario that we have is some physics, some mathematics, and some data. Now, of course, in weather predictions, that's what people do all the time. It's called the data assimilation problem. Of course, but as you know, they don't do it very well because the system is very complex and so on. I will try to present here how we can do this seamlessly and effortlessly using these neural networks, the data assimilation, and how we provide the closure of the missing physics of the process using data. So to that, I will introduce, as I said, PINS, physics-informed neural network. We wrote this paper a long time ago. They said it's very simple, and they didn't want to publish it. Now it's the most downloaded paper in the Journal of Computational Physics. So what is a PIN? So a PIN is a standard neural network. For those of you who work in this area, probably you've seen this. Let's say you're trying to find a function u of x comma t. So the input is X and T, and neural network is really a function approximation. U is a function of X and T. So you have some data, we call the data UI, and then this is the prediction of the neural network, and you take the least square, the mean square error, you try to minimize this, and by trying to minimize this, you find these connections in the neural network. Okay, these connections are what they call the weights and the biases of the network. And sigma is the nonlinear activation function. Could be a ReLU, or it could be like a hyperbolic tangent. Think of hyperbolic tangent. So it's just a different way of numerically computationally representing a function, but in an intrinsic fashion. But in order to find these connections, which are thousands of connections, you can have thousands of neurons. Each one of these is called a neuron. You need a lot of data, but as I said, we don't have lots of data in biomedicine. So we know some of the physics. For example, we know things are advected, diffused, and so on. And therefore, we can mathematically write down some parametric PDE of lambda, means it's a parametric PDE. So thankfully, in neural networks, people developed what's called automatic differentiation. Automatic differentiation allow us to take derivatives in space, time, and so on. So any differential equation that I'm trying to satisfy can be obtained by taking derivatives of the neural network. Remember, the neural network is a function u, so I take du dt by differentiating automatically without having grids and so on, like in conventional solvers, like in finite elements. I can differentiate the neural network directly, and therefore, without any meshes, any effort, you can actually obtain this equation, and you try to minimize the error in this equation, because u, which is the neural network, will go in here. It will not satisfy that equation. However, it will try to minimize it. So down here, if you can see on the bottom right, I have another term now, the mean square error of the residual of this equation. We'll try to minimize. So if I add up those two contributions now, this will be the physics on the right. This will be the data. So now I have blended data and physics together, and I can weight them. I can take the weighted sum of that. Then the neural network, this formulation proceeds by just finding the minimum of that objective function, which is called the loss function. So it's really very simple. I want to demonstrate how this is done. Let's say you try to solve this equation here. It's a PDE. It has time derivatives, nonlinear terms, second derivatives. So we never discretize a space or time. We have data which are basically some initial conditions, some boundary conditions. Notice that I have big gaps in my boundary conditions. So I cannot solve this equation with conventional solvers. However, with pins, you can do it, because you take these black crosses, the data. This is the first term I talked about. Then how do you construct this equation? So you construct it by take automatic differentiation, and then at random points, which I draw now inside the domain, the spatiotemporal domain, I can evaluate this physics term, and that physics term basically provides extra data. The data that we don't have are provided by the physics. Okay, so you can see these codes are very short, 10 lines of codes. A high school student works on this. Usually it takes one semester to learn how to solve this equation. Now, a high school student, literally speaking, a high school student, I wrote recently a paper with Jeremy Yu from Texas, 17-year-old, who solved these equations in 10 minutes using TensorFlow. This is TensorFlow. Okay, so how does that relate to what I was saying earlier? Well, again, this is the medical data. This is a video. Can I use the video synergistically with the physics, the mathematical laws, to extract quantitative information to see when this aneurysm will break? Instead of doing this on 100,000 processors, I want to do it on a laptop. Okay, so the data here, this is a paper we wrote in Science a couple of years ago with the title Hidden Fluid Mechanics. Hidden fluid mechanics because we use auxiliary data like visualizations. And the image here, the intensity of the image is going into this, which looks like an advection equation. And then I know I have a blood flow, so I know how to write the Navier-Stokes equations in the nonlinear form. viscosity depends on the strain rate. And then also I have incompressible, the blood is incompressible fluid. So I have this equation that I close the system together with the data. All these live in a same space. So I use the data to set up to basically train the network. And then since I train the network, I know the parameters of the network, then I can transfer knowledge to the velocity and the pressure, which are my primary unknowns. If I know velocity and pressure, I know the wall shear stress, and the pressure I know, I can compute the forces on the aneurysmal wall. Okay, so here, unlike in CFD, for example, where you have to take the entire geometry, here I can zoom in only on the aneurysmal sac because I don't need to know any boundary conditions here. I just told you earlier about this. Okay, so this is actually you can look up the paper in Science magazine that this is the concentration of the dye. We try to match it. This is in 3D. I just show a slice. And then in the process, we find the velocity, we find the pressure, and so on. I just want to show you this movie if I can. Here we go. So you can see here, what we learn is the flow inside the aneurysm without boundary conditions, and this is a CFD companion simulation to show that indeed we can do that. Of course, if you can do that, then we can compute the forces and so on. That's the question. From giant aneurysms back to micro aneurysms, I showed you earlier. Now we wanted to go back to a microfluidic lab with my collaborators at MIT. And here they built what they call microaneurysm on a chip. Basically, what they wanted to look at different sort of vessels and how these aneurysms are. And what you see here on the left is a movie with multiple aneurysms and real blood. Again, you don't learn much because there's no other measurements. It's just this video. So we wanted to use this idea of hidden fluid mechanics to maybe you can see here what is going on clearly. What we want is actually the stresses on the here, because that's what will determine the rupture. So we can do simulations, but we actually wanted to use the data to extract quantitative information. So qualitative inference of the 3D motion, although we are only looking at one plane where we strike the light. So we developed this, what we call AIV, artificial image velocimetry, where we basically, something similar I showed you earlier, we take the images, the experimental data, and then we also have the Navier-Stokes equation, so we can basically transfer the qualitative information to quantitative information. So now the gradients of concentration are very useful to identify the flow pattern and the pressure pattern, and we can do that in that plane. But in fact, so what we did is to show that we can get velocity profiles here, there, and unlike other techniques, here we can go all the way to the wall, and of course that's very important because we can compute the wall shear stresses, which is of great importance to. We can extend this to 3D by using the physics in 3D and one slice only or two slices, and just having the boundary conditions. Actually, you can extract quantitative 3D information from 2D planar information. And here we have another validation with CFD and molecular dynamics for this microaneurysm. So this is very powerful technique now because it can be used in many different contexts, as you can appreciate. And we work with people from University of Rochester now to measure the pressure and fluid velocity in the brain of a live mouse, or the CSF fluid. Okay, and just to conclude with the image informatics and machine learning, I found this video on YouTube 2 years ago, and I asked my postdoc, can you extract quantitative information from this video? This is now, I didn't know this person at the time, now he's become my collaborator, Thomas Berg from the company LaVision. German company. But basically, he was puffing with and without the mask to determine how far the droplets from his mouth would travel. So what we did is we took the video and used this hidden fluid mechanics technique. Down here, you can see where I zoom in. And basically use the same technique. We can now obtain quantitative information on the velocity field. What you see here on the video on the bottom right is, and here is corresponding pressure. So now I have the pressure field using the HFM method, hidden fluid mechanics, and also I have the velocity field. So we can determine that. I know in Florida, people don't like to wear masks, but masks are important because they can cut down the travel speed of droplets by 10 times. All right, let me switch gears again and taking some lessons from neuroscience and human neurons. We wanted to design a totally different neural network that can do more than approximation of solutions. It can basically discover a black box or discover an operator. If we're talking mathematics, it can discover operators. So of course, a neuron has these dendrites, these branches, has the soma, the trunk, and has this axon, and that's the output right here, connection with other neurons. So we design a neural network which looks like that. This is a branch. They associate with the inputs. It can have multiple branches, like the human neurons. And then this is the trunk associated with the output where the computation is done. And this is really the output associated with this part of the neuron. So we call that deep operator network because we're trying to approximate operators. What does that mean? Well, in mathematics, if you think about it, before a neural network, it takes data input and outputs data. Of course, what you have in between is the function. So that's what the neural networks do. This neural network, the composite neural network, is different. It takes functions and will output other functions. For example, it will take the cosine and find its integral. It will take the cosine and find, as an initial condition, find a solution of this operator. So because the input is a function, the output is a function, what we are learning is an operator, right? It's an operator in a very broad sense, a mathematical operator or another operator. So we actually, I didn't want to bother you with mathematics, especially early in the morning, but this is an important result we published in Nature last year that shows that there is actually rigorous mathematics that can support that we can approximate using these two neural networks. This is the trunk I told you, with a deep neural network, and a branch, the dendrites. We can approximate an operator G that takes a function U of X and maps it into a G of U of Y. So G is the nonlinear operator, whatever that is a continuous operator. It could be also discontinuous, but continuous operator. If you have one layer, a neural network with one layer, you can see what's going on. Basically, this is the affine transformation for the neural network. Then you pipe that into a nonlinear activation function. So this is a trunk. And then here, this is the branch. And then you take a sum of, this is just one, let's say, coefficient that you get from the input. The input is what you sample, the input function. And then this is the output. So we have now something that maps input functions to output functions. So for example, you can give it some boundary conditions and you can have the stress field on the output. And just to give you an example, a very elementary example is, let's say we're trying to train this DeepONet to learn how to do indefinite integration, 0 of x of some function u of t dt, okay? So basically we want to learn to go from u of x to the integrand s of x. Notice that x is from 0 to 1, it could be from 0 to infinity. So you can do Laplace transform, for example, to learn, so you can train DeepONet to do Laplace transform. So what you do is you take 10,000 functions and you evaluate s of x at only one point. That's the amazing thing. Although x is in this continuous space, you just need to evaluate the output at one point, which means you just need to do one experiment. For every excitation, you do one experiment, and then then basically you can train this network. The network will learn how to integrate. And here I show you that it learns how to integrate any function now with pretty good accuracy, 10 to the minus 5 error. Now, how do I apply this again to complicated phenomena like this project I have with Jay Humphrey from Yale University on aortic dissections? It's a R01 NIH project that we currently have. So we're interested in aortic dissections, which are basically cause the intima and the adventitia to separate, sort of delamination of a material, if you like. So that's a very complicated process. There's a hypothesis, in fact, by Professor Humphrey, that these gags, which are these pockets of fluid inside the microstructure, may be responsible for it. So there have been some experiments, in vitro experiments, that they pressurize like a vessel like that, and then they try to determine pressure versus volume of fluid and corresponding response, damage and fracture. And so it's basically a fracture. It's fracture, which is very stochastic and very difficult. So it's very computationally expensive to compute fracture, and you don't really know if it's accurate because of this multi-layer structure that we have here. So we idealize this for our purposes with the strats and some background metrics, and we produce a lot of data using phase field modeling. Down here you can see what this finite element simulations using did. It did a pretty good job, because you can see the microstructure and the delamination and the separation by this pressurized fluid. So we wanted to ask the question, because this takes a long time to do one of these computations, can we pre-train a depot net to learn how to solve this in 0.1 seconds? And it takes a little bit of time offline, because we need about 2,000 simulations. So you need to have patient postdocs to do this. But then after you do that, in the depot net, you give the microstructure, like an image of the microstructure and the displacement field. And then you obtain the damage field. From the damage field, you can obtain this pressure volume relationship, which looks, let me see if I go back here, this pressure relationship looks like this. Okay, now this is associated with the fracture, the broken strats of the underlying structure, and so on. So this is just to tell you that this can be done, for example, in many, many different cases. If you don't use a damage field, the accuracy is not very good, but basically with about less than 5% error, we can now have depot net that knows how to do dissections, and therefore I don't need to do huge computations. I can do this very quickly on my laptop. And just as a teaser, is unpublished work that is currently under review. We were doing, again, with Jay Humphrey at Yale and his great research group. They have this data for different genotypes of mice, five different genotypes. And we're looking at dissections and basically recording biomechanical tests. What you see here, and that I circle, is stresses versus stretches, right? So we have about 30 data points from 5 different genotypes. This is not a lot of data, actually, because you only have 4 data to identify which genotype this came from. So we had to do a lot of work to use depot net with autoencoders and data augmentation techniques. But now we can identify we can go back from, so we have this genotype to phenotype network that, given the genotype, it can sort of predict what type of phenotype you have. Or given the phenotype, like the signature, the biomechanical signature, I can tell you, or the network can tell you, which genotype is involved. And it turns out that aortic dissections for humans, of course, much more complicated, but the genotype plays very, very important role. And of course, other environmental and reasons, and also how you habitual behavioral reasons. Let me see how much time I have. Okay, sorry I packed this this talk, but I want to give you also some flavor of what bioinformatics can do. So I will switch now to type 2 diabetes. This is, of course, a a disease now that is more prevalent. The epicenter, believe it or not, is not the United States, is China and India. But we wanted to look at different aspects. We are doing rheology of blood of diabetic people. We are also looking at the balance between glucose and insulin. And we also work with doctors at the Beth Israel Medical Center to determine if we can predict in advance hypoglycemic and hyperglycemic events, especially hypoglycemic events. So I will give you a couple of examples. First, and this is something that could apply to any systems biology system. That is, here I have as an example the glucose-insulin interaction model. Of course, glucose is G here. We have monitors now that we can totally track the amounts of glucose in a diabetic patient. But there is this, in systems biology, we have these systems of equations, which are nonlinear ODs. Here, for example, this is the plasma insulin, some other type of insulin, and these are 3 auxiliary variables. So what you see here is a system of 6 ODs and 20, you don't see all that, 20 parameters, 20 unknown parameters. Now, this is an advantage and disadvantage, the 21 parameters. The disadvantage is, of course, that you have too many parameters. The advantage is that if you have enough data on glucose, you can possibly identify all these parameters and make it patient-specific. So this model would be patient-specific. So in fact, pins are ideal for solving this hybrid problem where we solve both for the dynamics, the glucose dynamics, which we don't know, but also the plasma insulin dynamics, as well as finding these parameters and make this patient-specific model for that patient. So what I show you here with the blue dots is data, okay? This is simulated data just to be able to compare, but we have real data, as I'll show you. So we have data from here to there, and in this time window, we can solve these equations using pins, and the parameters, the 21 parameters, is just added to the parameters of the network. So it's not a big deal to handle unknown parameters, but at the same time, we find the dynamics of the plasma insulin, the interstitial insulin, and these other auxiliary parameters. So I can basically now, after here, I can forecast. This is all forecast, and you can see there are 2 lines there because on the one of these lines is the what's called the exact, which is the MATLAB simulation of this in the forward mode, just for testing. And here in this peak, for example, we have a meal intake, and you can see the spike of insulin that people who are interested in intermediate fasting are talking about. Now, this type of networks are not simple. So we published a paper in Computational Biology to illustrate this. And so for different systems. So what you are solving is an ODE system that looks like that. It's on the right-hand side, you have a function of the state variables, X, time, and also P, a set of parameters. As I said, all systems biology situations can be casted in that form. And if you look at the loss function here, we have the data. This is the glucose. Here will be the physics, as I explained before. And you can see here the physics, it's a parameterized ODEs. So now this is unknown, but also the state is unknown, the I and the G. Of course, we have some data for G, but every 5 minutes, let's say. And the interesting thing here is that we had to change the neural network architecture to bias the solution of the network with a feature layer that we put here. And what we demonstrate in our paper is that depending on the systems biology case that you're looking at, here I'm discussing this glucose insulin system, but we look at yeast, we look at cell apoptosis, the death of cells, and in each case, this feature contains functions as features so that it will bias the network to go and approximate in a certain way, because this is not very simple dynamics. You have these oscillations and then you have these spikes. So neural networks have a hard time to do that unless you have millions of data. So anyway, that's a technical issue, but if you're interested, you can find our work on PLOS published. We also have a tutorial on how to do this in systems biology. There's a publisher that asked us to write a tutorial, which we also have on the web. Now, switching gears again, and I want to talk about something that is useful not to researchers, but to clinicians, and that is from the data that you have from the monitor of the glucose, can you predict in advance, let's say half an hour in advance, 15 minutes, an hour, can you predict if you will have a hypoglycemic event, hyperglycemic event, or in between? So you have, this is sort of a classification problem, if you like. The challenges here, of course, is that you have relatively small data. You have one patient that you're looking at, and then the data is in balance. In other words, most of the times the patient is at the normal state, maybe because of eating some tiramisu or other sweet stuff, can get hyperglycemic. But hypoglycemia is it's a kind of a rare event. In fact, it's unwanted, right? Because then the patient has to be hospitalized immediately. So actually, hypoglycemia is what we are after. Unfortunately, we don't have data. That's like a rare event. So how you deal with that? So that's what I want to tell you. But first, let me tell you the setup. The setup is we have this monitor. We get data every 5 minutes, let's say, from a patient. And we want to look at these 3 different states. And you can see there are barriers that in units 70 or 80 or 180, depending on where you put the threshold, you have let's say below here, below 80 or 70, you have hypoglycemia. So what we did is, because of we only had 40 patients, we have 40 type 2 diabetes patients, and we had 120 hours glucose data. What we did is we pre-trained a neural network for 39 of them, and then we use transfer learning for just a few initial data from the 40th patient to make it specific to that patient, and then we try to predict what will happen to that patient. And then for another patient, we rotate the 39 patients. So here we have to pre-train a network and then also do some what's called transfer learning. So we built a neural network that is, of course, the input. It's the blood glucose. Then we have a feature block, which is a neural network, and the inference block, which is just like the feature block I showed you before with the sines and cosines. Now we have a neural network which is of different type, like this RNN is recurrent neural network. It keeps track of memory. Convolutional neural network, something else that's called self-attention neural networks that allows inputs to interact and so on. So that's one unit. Then we have a feed-forward neural network, and then we have the output. What we did in transfer learning is so you can see here, this is basically what we learn. Then when we do the transfer learning, we decide to leave some of one of these networks undetermined partially, so that the new data from the new patient can be used to make it patient specific. So when you see the dots here, we let both blocks undetermined. In this case here, we fix the feature block, but we let the inference block being determined by the data of the 40th patient, if you like. Okay, so that's what transfer learning is very important, because you never have enough data, as I said. So it turns out that all these variations of different neural networks with different features work well. CNN and self-attention works better. This is for a two class classification. This is a 3 class, but you can see accuracies of 95 and above. It's a little more, so after we train this, we published our paper in Nature Digital Medicine. The reviewers asked, can you apply this now to other data? They suggested the Ohio type 1 diabetes, not type 2 that we had. So indeed, we compare our pre-trained network for 30 patients there, and we found that indeed we beat the state of the art using this pre-trained network which requires very little data from, as I said, just in the beginning of the time record for the new patient. So we achieve 95%, 96% accuracy. I just want to make this point about, I presented this type of work to NIH about challenges in AI for biomedicine, and I pose this as a big challenge: data augmentation for imbalanced data. Typically, you're interested in some state like a hypoglycemia, and for the state that you're interested in, you have the least amount of data. So here, schematically, I show you that no hypoglycemia, you have this much data. Hypoglycemia, you have this little data. In standard statistics, this is solved by sampling more often the hypoglycemic, the minority class. But that gives you huge biases, and people have published a lot of wrong results with that. So this is repeating the minority data, as I told you, but now with machine learning, there are many techniques. For example, one can interpolate. This is a method called mix-up. They can interpolate the inputs and also corresponding outputs. So you have labeled data, which is interpolated. One can perturb and include Gaussian noise in these samples, create perturbations. And this technique, which is modern technique, it relates to generative adversarial network and generative adversarial modeling, which basically uses sort of sophisticated perturbations of realistic data to create new samples. Well, that's another data augmentation technique. So now if we look at sensitivity, PPV, specificity, and so on, usually the doctor wants to have a sensitivity which is more than 85%. Here with 80%, so by, let's say, if we look at this case that I like, if we increase, for example, the minority data fold and use this time gun, you can see we can go from 80% in sensitivity, we can go up to 90%, of course, at the expense of the PPV. So there's a balance that you have to strike, but there are ways out there that one can utilize in this type of work. And I'm about to finish here. I just want to finish with the mechanistic modeling. So mechanistic modeling, I didn't have a chance to talk about all the things that we've been doing in the last 20 years. A lot of them with my longtime collaborator who used to be at MIT, Subra Suresh. Subra is still is now a president. He was the NSF director for a while, then he became the president of CMU. Now he's the president in Singapore at NTU. We're still working together. We just published another paper, but we put together this idea of creating a first principles virtual models, digital twins for red blood cells, if you like. And we had IBM to collaborate with us. So now this is a paper jointly published with Subra Suresh and my group. So he was doing microfluidic experiments, and so we can have in silico prediction of the human viscosity. We published this in 2011, but we can also create diabetic virtual blood, as you can see, and predict from first principles the viscosity. Now you say, how do you know that this is diabetic blood? So we have a barrage of tests. For example, in the lab at MIT, they will do these experiments, microfluidic channels, they do atomic force microscopy, they do micropipettes, and then we set up similar simulations using molecular dynamics, something we call dissipative particle dynamics. And then we can do similar things by comparisons. And this is not just one case, but many, many cases we let cells going through the through these micro channels, 2 to 3 micro channels, so we can obtain, for example, the viscosity of the membrane, the shear modulus of these red blood cells, the shape, of course, they're a little bit more rounded, so we can have actually virtual blood, or we can have sickle cell blood, or malaria blood, and so on. So we have many papers on that show. So we use microfluidics to extract information, then we build this from first principles red blood cells, and then we have populations for red blood cells for rheology. Now you say there are other complications especially in diabetes. This is a microfluidic experiments of an assay. You're looking from above in red blood cells of healthy individuals or slightly obese, where fibrinogen is relatively low, you can see all this can go through these obstacles, all these red blood cells. However, for diabetic patients, you form this rouleau because the blood is sticky, or you can see when you increase the fibrinogen level. So then you have these rouleaus, and as they go through, they break up. Now, from this information, we can actually infer the aggregation forces. How strong are the bonds for these rouleaus? And then when we build these now virtual digital twins of this, we can obtain, this is now all simulations, we can obtain rouleaus that break the same way as in the experiments. And therefore, we know that we have the right rouleaus, we have the right forces, which are very difficult. So in direct measurements and doing statistics, counting how many of these cells will become doublets and so on. And so, okay, so with that, I just want to give you the big picture. And the big picture is we want to advocate the integration of mechanistic modeling. We don't want to abandon what people have been doing for various methods at different levels at the organ level, at the cell level, and so on in between. With image informatics, I show you many examples, and bioinformatics, the diabetic example. And then altogether, this could lead to a digital twin. And what, just before the pandemic, we had another workshop with all the heads of engineering departments, Mike Miller from Johns Hopkins and San Diego UCSD organized this, and collectively we came up with this name, AcuMedicine. How you can, I was advocating for digital twins, so there will be a thesis publication soon on that. We're sort of slowed down by the pandemic, but the idea is that you use all sort of data. No data is left behind. You can use static data, real-time data, like I show you for the diabetes an example. Then we can use the biology-informed neural networks, or what I call the physics-informed neural network. We can use mechanistic modeling, and then all that worked synergistically to do real-time prediction and decision making. Here on the left, I also have this picture of, let's see if I can go back, of full simulation in 1D of the arterial tree, so we can look at effects on distal places where things would happen. So as I said, this notion is not, this sort of idea has not been published yet, but this is what we're after. And if you are interested in pins, we have created an alphabet of pins for all sorts of PDEs, but there's a library. This library here has been downloaded 300,000 times from GitHub, and basically can be used as an educational tool or as a research tool. It's all open source in TensorFlow or PyTorch. And you dial in it's called DeepXD, DeepX for any differential equation. You dial in an ODE or a PDE or a mix and some data, and you can get solutions very quickly. So with that, I'd like to stop here and take any questions. And thank you very much for your attention.
Very nice. Thank you. Thank you. This is giving us a lot to think about. Let me start with some audience questions here. We have one from Nicholas Mohammed. Your work is extremely interesting and very futuristic. How do you think these technologies could be applied to analyze electrical activity in the brain, possibly with applications in brain-computer interfaces?
Oh, okay. Yeah, that's a good question. I mentioned the pins, which will take the electric signals as data, and then it will take some parameterized model that you hypothesize, and you can actually find all the dynamics plus these unknown parameters of your model. So I would think something like that. I haven't done, but I think something like that would be really very appropriate. And that's what I sort of show you with the glucose insulin system of equations, right? That it was not patient specific. We made patient specific with just one-time series. So having the electric signals will basically give you the data. If you can relate that to other quantities of interest and hypothesize a model, you can do that, and then you can ask what-if questions very quickly, actually.
Very nice. I think I will, okay, here, another question coming in. Interesting presentation. Are there examples of pins to natural wind applications?
To not.
Natural wind applications, or other examples in turbulent flow?
Oh yeah. Oh, okay. Okay. Yeah, yes. There are actually not just my group. There's many people around the world are using pins for all sorts of applications, including turbulence. There's several papers in. We have published a paper called NSF-NET. NSF doesn't stand for National Science Foundation, but stands for Navier-Stokes Flow Net. So NSF-NET does that. It's kind of DNS. There are other people who use this creatively, just use some measurements and the Reynolds average Navier-Stokes to close on very naturally without resorting to ad hoc assumptions or closure models like K epsilon that never worked for the last 50 years. So there's a paper by Ricardo Vinuesa that shows in the Journal of Fluid Mechanics that he has some measurements on the boundaries data, and then from that is enough to actually close the system and get runs, make Reynolds happy, because his Reynolds average equations worked actually okay if you close it with the right data. Yeah.
I think I will abuse my position as panelist to ask some questions of my own here. In the PINS framework, it seems to me like there would very easily be a tension between the loss function that reconstructs the data and the part of the loss function that enforces the physics that you know, the differential equations.
Yeah.
So, right, especially because these are underdefined problems.
Yeah.
So I mean, what are the tricks that we need to play to make sure we play well together? Does the learning schedule change?
Yeah. Zach, this is actually the very important question. We when we first published our papers, we kind of knew that you have to weight manually data versus physics, and depending on like how stiff was the problem. Let's say you have boundary layers, stiff boundary layers, and you have to do that, and that was important. In fact, for multi-scale problems that we're dealing here, that's very important. So I didn't come up with a solution, but there's a professor in Texas A&M. His name is Ulysses, although he's Brazilian. I call him Clever Ulysses because of that. So what he did, he actually introduced weights in front of the loss of data, in front of the loss of the boundary conditions, in front of the loss of the physics, the equations. And these weights depend on space and time. Now, so these are unknown weights. So now he adds to the weights that he has for the weights and bias of the network and all the parameters, the physical parameters, he also adds these weights. So what he reformulates the problem. So he's solving a steepest ascent, it turns out, for ascent, the steepest ascent for these weights, but he lets the data, the evolving data, capturing those weights. And amazingly, these weights actually are physically relevant, because if you look at the physics, if you have steep fronts, if you have a multi-scale structure, the weights follow exactly that. So the weight change in space-time, and it turns out, although you add more unknowns now, it turns out the whole thing converges faster. Less number of epochs, because you're going towards the global minimum faster using this technique. So it's called self-adaptive weights, and there's a paper on the archive by Clever Ulysses. His name is Ulysses Bragoneta. So that's sort of the answer to it. I have tried many things in our group, and we finally adopted his method. Works really well, especially for transient dynamics, like the dynamics I show you with the insulin, that you have the spikes and so on, where the weights will capture either high frequency or the spike and so on. You don't need to do actually all the special features that I talked about. But yeah, that's very important, and I think that sort of answers this question really.
I'll have to save the dozen or so follow-up questions that just generated in my mind for the individual meetings later. But thank you again for this really exciting and I think provocative presentation based on the comments I'm seeing here. So thank you again for speaking with the department. We really enjoyed it.
Okay, thanks.